So in this video, we're going to be looking at the different kinds of factors dealing with probability. This is going to cover a lot of different topics on probability, so you might need to come back to it every now and then as we go through it in class. I'm going to try to go through it in the order we tackle it in class, but there might be some things a little bit out of order. So the first thing about probability is that there's actually two different kinds of probability. The first and probably most common one is theoretical, which is basically based on the factors of the situation, which is like if you're rolling a die. So if you're rolling a die, you want to know what's the chance of getting a 6? Well, you know that's going to be 1 out of 6. Well, how do you know it's 1 out of 6? Well, because there's one number 6 out of 6 total numbers. So 6 is the total number of outcomes, and 1 is the target number of outcomes. There's only 1 6 that we want. So theoretical means you don't actually have to try it. Theoretical means you can just hear it, look at it, and solve it yourself. And the formula for this is usually written like this. It's a fraction, of course, and it is the number. I'm going to try to write this as best I can. I'm using a mouse here. So number of target outcomes, which is what you're looking to get, in this case the 6. And this is going to be divided by what's on bottom, which is the number of total outcomes, which is everything that could possibly happen. So how many different ways could rolling a die happen? Well, there's 6 different ways. 1, 2, 3, 4, 5, or 6. So the number of things you want to have happen divided by the number of things that could happen. Again, in a die, it's 1 out of 6. If I was flipping a coin, what's the chance of me getting heads when I flip a coin? Well, it's 1 out of 2. There's 1 heads out of 2 total possibilities. Okay. Oops, total. Probably misspelled that the other time too. Total. And another one would be drawing a card from a deck, which is another popular explanation. So if you know that there are 52 different cards in a standard deck of cards, there's 52 different cards in a standard deck of cards, what's the chance of you pulling the ace of spades? Well, there's 1 ace of spades out of 52 total cards, so it'll be 1 out of 52. What's the chance of you pulling an ace of any color or of any suit? So what's the chance of you just simply pulling an ace? Well, there are 4 aces in the deck, and there are 52 cards total, so it'd be 4 out of 52. Now you actually can reduce this and make it 1 out of 13. Or another example would be if you have a classroom, let's say there are 7 boys and 5 girls, and I say, what's the chance of me picking a girl? Would be 5 girls out of 12. So that'd be the chance of picking a girl, or the probability. It would be 5 out of 12. Again, I don't have to actually try it out. I can just know based on the situation. Experimental is a little bit different. Experimental is the probability we get based on the results of experiments or trials that we have done ourselves. So usually the formula is like the number of successful trials. I'm going to misspell this, my bad. And this is divided by the number of total trials. Again, my handwriting a little bit messier than normal because I'm trying to write with the mouse here. It's a little bit difficult, but bear with me. So the experimental is based on the number of times you get what you want divided by the number of times you tried. So this is used when you don't know how the factors play out. So for example, what's the chance that this medicine will cure your illness? Well, I really don't know the probability unless I actually have tried it out on a whole bunch of different people and see how many times it works and how many times it doesn't. Insurance companies do this for car crashes. You want to know what's the chance of you getting in a car crash? Well, they look at how many crashes have happened for people in your age group and how many crashes have happened for people that are similar to you, and they apply that to you. So I can't actually come up with a theoretical probability of what's the chance of you getting into a car crash. I simply have to go and say, okay, how many times has a car crash happened for people that are similar to you, and that's going to be what I apply to you. So experimental is used for when you don't know what the factors are. I wouldn't use experimental for rolling a die because I know what the factors of a die are. A die is a 6-sided object. Each side has an equal chance of happening, so it's a 1 out of 6. I don't need to actually run the experiment. I just know off the top of my head what the probability is. Now, if the die was weighted in some way or altered where one side came up more than the other sides, I didn't know exactly how much more, then I would have to use experimental because now I no longer know what side's going to come up more than the other. They're not all equal anymore. So then I have to run the experimental test and roll the die, tens of thousands of times to see which side has a more likely chance of coming up and what the probability of each side coming up is. So let's look at these in practice here. A bag has 2 red, 3 green, and 4 blue marbles. What's the chance of choosing a red marble? So this is theoretical because I know the factors. 2 red, 3 green, 4 blue. I know exactly what can happen. I'm either going to pick a red, a green, and a blue. I know exactly how much of each there is to possibly get. So what's the chance of picking a red marble? Well, there's 2 red marbles that I know are in there out of 9 total. So my probability is 2/9. Or if you want to make that to a decimal or fraction or a percent, you can. Just take 2 divided by 9, get the decimal, and then times it by 100 to get the percent. So that's theoretical there. Again, I know exactly how many red marbles there are. I know exactly how many marbles total there are. I know everything about the situation, so I can make my probability based on that. Same thing for B. What's the chance of picking a non-green marble? Well, how many non-greens are there? Well, there's 2 red and 4 blue, so that's a total of 6 non-greens out of 9 total. I can reduce both of those by dividing by 3, and I get 2/3. And that is the probability of picking a non-green marble. Again, 66% if you want to put it into a percent form. And again, I know exactly how to get that without having to choose it myself. I don't have to actually run this experiment to figure out what it's going to be because I know what the factors are. Now the next one's a little bit different. It says a cold remedy is given to 1,200 patients. If 850 of them have their colds cured, what's the chance the medicine will work? Well, I don't know exactly what the chance the medicine will work off the top of my head because I really don't know the factors. I don't know the likelihood of it happening. But I can figure it out by looking at what I've tested so far. So far, I've tested it. My total number of trials, my tests, are 1,200. I've tested this cure 1,200 times. 850 times, it was a success. It worked. So what's the chance of me getting this to work? Well, it's 850 out of 1,200. If you want to reduce that here, you cross out the zeros. You get 85 out of 120. And you can further reduce that by dividing by 5. So that'd be 17. Whoops, not 15, 17. Ah, there we go. 17 out of 120 divided by 5, that'd be 14, I believe. Let me check that real quick. I'm not quite sure on that. 24, sorry. Got the right last number, but the wrong first number. And I don't believe this can be reduced anymore. So that would be where we're at. So the chance the cold remedy will work is 17 out of 24. Because I started with the number of times it worked divided by the number of times I tried. Which, if you want to calculate the percent, is about a 71% chance, which is not too bad, I guess. It's over 50. But again, I couldn't tell this right away. I need to actually try out the remedy and see, okay, I'm going to test it on 1,200 people and see if it works, and then I can say how well it's worked. Now, you might be saying to yourself, what if you tested it on more people? Wouldn't that change your probability? And the answer is yes. So the thing about experimental is that you have to test it a large number of times. Even 1,200 is probably a little small to get a good, accurate experimental probability. If you want to get a good, accurate experimental probability, you have to test it, tens of thousands of 100,000s of times, and the more you test it, the better your experimental probability will be. So experimental probability is heavily dependent on how many times you actually tried it out. You can still do it with like 500 trials, but it might not be that accurate. The more times you try it out, the better your experimental probability would be. Now, as you notice, a lot of these deal with, both formulas back here, deal with total number of stuff, total number of trials, total number of outcomes. The problem with that, especially with this one here, is that getting the total number of outcomes for a large situation can be a little difficult. If you have a really big situation with a lot of different factors involved, getting the total number of things that can happen is kind of hard. So for example, if I had a sandwich shop and I have 5 different choices of bread, 4 different choices of meat, and 16 different choices of toppings, how many different sandwiches can you make? Well, that's going to take a while to figure out, to go through every single type of sandwich, every single possible combination, and figure out what I can do there. So to help us with that, we have this thing called the FCP, or the fundamental counting principle. Basically, this is a way for us to calculate what the total number of outcomes are in very large situations. So the total number of outcomes is basically how many things could happen in the first category, how many things could happen in the second category, how many things can happen in the third category, and so on and so forth until you run out of categories, and then you times them all together. So for example, in my sandwich thing, I had 5 different types of bread, 4 different types of meat, and 16 different types of toppings. Let's say you can only choose one of each. Well, my FCP says the number of sandwiches I can make, the number of different sandwiches I can make, is 5 choices of bread times 4 choices of meat times 16 choices of toppings. Multiply that together, and that's how many different sandwiches I can make. Again, assuming I can only choose one of each. If I can choose more than one of each, then we have a little bit more difficult problem on our hands. But for right now, we're just going to choose one of each. So multiply all the different things that can happen in the first case times the second case times the third case, and then you get how many things can happen in total. So for example, 7 people in a class that are to be arranged in a line, how many different lines can be made? So how many different ways can I arrange 7 people in a line? Well, it might be helpful to actually draw blanks to represent your cases. So we have first person, first case, second case, third case, fourth case, fifth case, sixth case, seventh case. Seventh case. Can't speak today. A little bit stuffy here, so I apologize for my voice. So there's 7 different possible categories, 7 different possible positions. How many people can I pick for the first position? Well, 7. One of the 7 people are going to be in the first position. So there's 7 different possible people that can be in the first position. Now, once there's a person here, they can't be here. You can't have the same person 2 spots. So how many different people can I pick for the second position? Well, only 6, because one of them's over here. And this trend goes on forever. How many different people can I pick for the third position? Well, only 5, because 2 of them are over here. And then 4, and then 3, and then 2, and then there's only one person that can be in the last spot. So there's 7 different possible choices for the first, 6 for the second, 5 for the third, 4th for the fourth, 3rd for the 5th, 2 for the 6th, and 1 for the 7th. I'm going to multiply all these together, and that will get me how many different possible lines I can make. Now, this also works if you work backwards. So if you did the last spot first, you get the exact same amount because multiplication works both ways. It doesn't matter whether you go forwards or backwards or sideways or middle out. You're going to get the same answer either case. So this is 5,040 different possible lines I could make with these 7 people. There's 5,040 different possible ways I can arrange these 7 people in a line because I just multiply all the cases together. Now, by the way, when you have this sort of case where you multiply from one number all the way down to 1, so 7, 6, 5, 4, 3, 2, 1, or if for some reason you had like 9 times 8 times 7 times 2 times 1, if you multiplied all the way down from 9 or 10 or 5, that's called a factorial. So this right here, the 7 part, could be written as 7 factorial with an exclamation mark. So this right here means exactly this. Means times all the numbers from 7 all the way down to 1. Not 0, because 0 would just make it all go to 0. But this little exclamation mark means start this number and multiply it to everything below it all the way down to 1. So 9 factorial would be multiply 9 to everything down below it, ending at 1. Number 2 is like the sandwich that I gave. You have 3 flavors of ice cream, 5 different toppings, and 2 sauces. You want to figure out how many different combinations can you make if you only get one item from each. Well, you have 5 different toppings times 2 different sauces. Whoops, I forgot the ice creams. It doesn't have to be in order, but I'm just going to do it just to make sure it's consistent. So 3 ice cream flavors you choose first. Then you choose one of 5 toppings. Then you choose one of 2 sauces. What's that going to make? Well, 3 times 5 times 2 is going to be 30. So there's 30 different possible combinations of desserts here that you can make from this list. Again, category 1 times category 2 times category 3. And this one's a little tricky. It says 3-digit passwords. So 3-digit means 3 numbers. So 1, 2, 3. We have 3 spots. We're going to use the numbers 0 through 9. So this is a total of 10 different numbers. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. There's a total of 10 numbers there. For each spot, you cannot repeat the numbers you use. How many different combinations can you make? Well, okay, how many numbers can I choose for the first spot? Well, one of the 10. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. How many numbers can I choose for the second spot? Well, I can't choose the same number because I can't repeat, so it's only going to be 9 different numbers I can choose for this one. And then again, I can't repeat either of these two numbers, so it's going to be 8 different numbers I can choose for this one. So I'm going to times these together and get 720 different possible passwords I can make from this combination. So I cannot repeat numbers, which means that each spot is going to have a different amount. If I could repeat numbers, if it says you choose the numbers 0 through 9, 3 spots, you can pick any numbers you want and use it as many times as you want, then I would do 10, 10, 10 and multiply it together. But since I cannot repeat numbers, it's change based on each spot. Now, this dovetails into something called compound probabilities. And compound probabilities is simply when you have two different situations going on at the same time, and you want to figure out what's the chance of this pair of outcomes happening together. And it's done very, very similar to the FCP. So let's say you flip a coin, and then you roll a die. What's the chance that you get a heads and roll a 5? So it's a compound. It has two different spots, heads and 5. There's two different probabilities going on here. I want to know what's the chance of them happening together. Well, what's the chance of you getting a heads? Well, that's going to be 1/2, 1 out of 2. Theoretical again. What's the chance of you getting a 5? Well, that's 1 out of 6. Again, theoretical. So what's the chance of you getting a heads and a 5? Well, just like the FCP, we're going to multiply together. Case 1 times case 2. It works with probabilities as well. And you get 1 out of 12. Because remember, you multiply the top, 1 times 1 is 1, and then multiply the bottom, 2 times 6 is 12. You do not need a common denominator for multiplying, remember. So the way you figure out compound probabilities when there's a lot of different situations going on is you break it apart into case 1, case 2, case 3, case 4. You find the probability of each case separately and then multiply it all together. So I kind of already dovetail here, but the chance of rolling a heads is 1 out of 2. Chance of rolling a 5 is 1 out of 6. So together, as we said, it's 1 out of 12. Oops, 1 out of 12. If I want the chance of rolling a heads, let's see if I do a different one here. What's the chance of rolling a heads? 1 out of 2. And rolling an even number on the die. Well, how many even numbers are there on a die? Well, there's 2, 4, and 6. So there's 3 even numbers out of 6 total, which gives me 1 times 3 is 3, 2 times 6 is 12, 3/12, which, if I reduce, gives me 1/4. Just like that. So again, break it down to cases and then multiply them together. Now there's one more different pair of probabilities to look at, and that's a dependent versus independent. So dependent probabilities is when you have a compound probability, but one probability impacts the other. So the first case actually impacts what can happen in the second case. It alters the situation. For example, these two, the one we just did, both of these are not dependent probabilities because it doesn't really matter what I flip on the heads. Rolling a 5 is going to happen its own way regardless. If I flip the heads, it doesn't make my chance of rolling a 5 any better or worse. It's the same. Dependent probabilities actually change the probability of something can happen in the second or third or fourth case. So for example, this is often called without replacement. So the same marbles again, 2 red, 3 green, 4 blue. So we have 9 marbles total, right? You're going to pick 2. If you do not put the marbles back, what's the chance that you pick a red and then a green? Well, again, let's do case 1, case 2. So case 1, case 2. Okay? And then we're going to multiply them together, remember. So what's the chance of me picking a red? Well, there's 2 reds out of 9 marbles total, so it's 2 9s. Now, if I keep that red marble in my hand and I reach in with my other hand and try to pick a green marble, what's the chance that I get a green marble? Well, there are still 3 green marbles, but there's no longer 9 marbles in there, are there? Because I have one of them in my hand. I have one of the red marbles. So now there are only 8 marbles in there. So the chance of me getting a red and a green, the red probability is very general, but the second probability has changed because I'm keeping the marble without putting it back. I've altered the status. I've altered the situation so that picking a green marble is now a little bit different than it was before. Now I'm still going to multiply them. 2 times 3 is 72. Or sorry, 6. My bad. Got a little ahead of myself there. And 8 times 9 is 72. I can divide both of these by 6, I believe. And I get 1 out of 12 as my probability. So in this case, case 1 changed what could happen in case 2 because it reduced the number of marbles in the bag because I didn't put it back. So dependent probabilities change what can happen after they have occurred. And I can do this with 3 or 4 or 5 different cases, each one being different depending on how I pick my marbles and whether I put them back or not. Now, the other one, like what we did before, is independent probabilities. These are when the events do not impact what happens after, often called with replacement. So you're putting the stuff back. You're resetting the status every time. So again, we have case 1, case 2. Same situation. 2 red, 3 green, 4 blue. You're going to pick 2. What's the chance of you picking a red and then a green? What's the chance of you getting a red? Well, still 2/9. Now it says here, I'm going to put that back. And what's the chance of me getting a green? Well, in this case, it'd be 3/9. Because there are still 9 marbles in there because I haven't held one back yet. I put the marble I picked back in the bag, so I reset the situation. So now there are still 9 marbles in the bag. 3 of them are green, so it's still 3/9. Again, I'm going to multiply them together. I get 6/81, which I'm then going to divide by 3, which would give me 2/27. My probability of getting a red and then a green in this case. So this is independent because whatever I pick first doesn't have any impact on what I'm going to pick second because I reset the case each time. Whereas this one was dependent because depending on what I pick first, that's going to change what could happen in the second case because there's going to be one less marble in there. There's going to be one fewer marble, so case 2 has been changed. And if I had a case 3, that would also be changed because I'd have 2 marbles out now and I didn't put them back. So now case 3 would be even changed further with only having 7 marbles in the bag. So if they're dependent, you have to kind of think, okay, between each case, what has changed? If they're independent, you don't. So that covers probability. Again, a lot of different facets to this. So again, don't be afraid to come back and look at different parts as we go through in class. Other than that, I hope you enjoyed the video. Have a good day.